Well, good morning, everybody, and welcome to class. Today, we are going to take the next step in this process of figuring out the structure and organization of the periodic table. And what we're going to do today is we're going to talk about how the structure and the patterns and the organizations that we learned about last time and then we reinforced during the lab that we did. We're going to figure out how these patterns and organizations lead to some interesting things about the way these elements interact as they come together to form compounds. So with you right now, you should have your periodic tables probably pulled out of your binder and easily accessible. And in addition to that, you should have the notes page that was made available to you. So as we get started today with this introduction to bonding, what we need to do first is we need to do a brief review of a couple important ideas that we learned last time and the day before in class. So, as you remember, as we were looking at the periodic table, we talked about the idea that the periodic table has this stair-stepped line that runs through what is essentially the P sublevel. And we talked about the idea that on the left-hand side of this line, we have the metals, and on the right-hand side of this stair-stepped line, we have the non-metals on the periodic table. And we remember that because of the location of the line, there are much more metals. There are many more metals than non-metals on our periodic table because our universe is made up of a predominance of elements that are actually metallic. Now, you may remember from class last time, we learned what that actually means. We learned what does it mean to be a metal and what does it mean to be a non-metal. So why don't we take a couple seconds and review those ideas so that we can draw on them as we move forward today. So first of all, thinking about the metals, we remember that all of the elements in group 1 have one valence electron. Everybody in group 2, the alkaline earth metals, they have 2 valence electrons. And then you probably also remember that all of the transition metals have 2 valence electrons because the d electrons are not valence. So the metals don't have very many valence electrons. The other thing we know about the metals is that as we move from left to right, remember the elements get smaller, the nucleus gets stronger, and as a result, the elements are drawn more closely together. And so what this means is over here on the left-hand side of the periodic table, these elements are big, and therefore they are weak. And as a result, they give away electrons. So guys, again, in summary, all of the metals are big, weak electron losers. And then the opposite is true for the nonmetals. The nonmetals on the right have 4 and 5 and 6 and 7 and even 8 valence electrons. They are small and they are strong, and as a result, they tend to gain electrons. So again, guys, metals, big electron losers. Non-metals are small electron gainers. So this then provides the foundation for what we're going to build into today. And so guys, in order for you to understand what we're developing into, it might be helpful to go back to a day that we had in September. And when we first encountered this idea of elements, we talked about the idea that elements are species, they're substances that contain one type of atom. We've done so much talking about protons and neutrons and electrons and all these other ideas. But then you may remember from there we started to talk about compounds. And guys, this is actually the jump that we're going to make today. We understand there are these things called elements all organized on the periodic table. And today we're going to start talking about compounds. And this then leads us to the title of what we're doing today, because today we're going to do an introduction to bonding. And bonding is the thing that turns elements into compounds. And so everything that we're going to talk about today talks about this idea of bonding. But in order for you to do this, you need to draw your attention down here to this area of our pyramid, and we need to remind ourselves about what we already know about the elements. And guys, that would simply be what we reviewed just a second ago. We know that when we talk about elements, we could be talking about metals. We could also be talking about nonmetals. And when metals and nonmetals come together, depending upon the pairing, we then get compounds. And guys, today you're going to learn that there are actually 3 different types of compounds. There are salts, there are molecules, and there are metallics. And this then lays out for us our challenge for today. Guys, we are going to figure out, why is it that when some atoms bond together, they make compounds that we call salts? Of course, you're familiar with table salt, but you're going to find out today that there are thousands of different types of salt, of which table salt is one. Then sometimes when atoms bond together, they turn into compounds, and we're going to discover why that is. And then sometimes when atoms bond together, they turn into what we call the metallics, and we're going to find out why that is as well. So in order for us to do this, let's lay out even more clearly the challenge for the day. And guys, it's simply this. Why is it that when sodium and chlorine bond together, chloride bond together, they turn into table salt? But when carbon and oxygen bond together, they turn into a gas which then condenses in the air and it looks like a cloud. We call that carbon dioxide. But then, guys, interestingly, when elements like copper and zinc come together, they turn into what we call the metallics, and this particular metallic, which is brass. So again, why does sodium and chlorine form sodium chloride while carbon and oxygen forms carbon dioxide and copper and zinc turns into something like brass? Well, what you're going to find out is that this defines the different types of compounds that exist. You already know that NaCl is a salt. It's table salt. Carbon dioxide is what we call a molecule. And then finally zinc and brass together, which makes, zinc and copper together, which makes brass, is a metallic. So why is it? Why is it that some element pairings form salt? Why do some form molecules? And why do some form the metallics? That, guys, lays out for you what we're going to do today. But before we do, we need to share some terms and some definitions that you need to be aware of. And so that's where we're going to continue today. So now, guys, looking at your notes page, this is where you are then going to begin taking notes. Guys, what you have in front of you there at the top of your page, which looks like this, is actually a representation of a water molecule. You might know that the big guy on the right is oxygen, and the 2 smaller guys are hydrogens. Those larger circles represent the valence electron clouds. And then the smaller circles in the middle, of course, those are the nuclei. So in order for you to be able to identify the parts that you need to know, what we need to do is we need to draw lines that connect the nuclei of these atoms. So please do this with me. And as you've drawn these lines, what you have actually identified are what are called the bond axes of this molecule. So a bond axis is defined as an imaginary line that connects the nuclei of the atoms that are bonded together in a molecule or a salt. And then, guys, after that, if you would draw in the blue arc that has come up on the screen in front of you. Guys, this blue arc, as you know from math, represents an angle, and specifically in the context of bonding, this is what is called a bond angle. So we have the bond axis, and where those intersect, we call that a bond angle. Now guys, the next thing that you're going to draw in, which is a little bit harder to see, is actually this distance right here. So you're going to draw a line that goes from the nuclei to the valence electron cloud in this molecule. Now, hopefully you're looking at this and you're thinking to yourself, wait, I already know the name of that. That is actually the atomic radius of that atom. And guys, that's true, but for one problem. The problem is that now this atom is bonded to another atom. And when that happens, the radii changes a little bit. So instead of being an atomic radius, this is what is called a covalent radius. And the covalent radius is actually the radii of the atom when it's bonded to a different atom. If you look at some point at your periodic tables on the back, you'll notice that the covalent radii are given as well. And then guys, this leads us to our next and final thing that you need to know, which is actually this distance. If you didn't see that come in, we're now talking about this distance here. And that distance is the distance between the nuclei. And that also has a name. That is called the bond length. Now, one of the things that you're going to need to be able to do today is calculate bond lengths. But I suspect a lot of you see this, that if we know this, the covalent radii, in this case of oxygen, and if we know this, the covalent radius of hydrogen, we simply add those together, and that gives us the bond length. This is what that looks like mathematically. So bond length is equal to sigma, the covalent radii. You probably know from math that sigma means sum, which simply means to add up. So the bond length is equal to the sum, or the added together, covalent radii. So there you have it, guys. These are the terms and definitions you need to know. You need to know bond axes. You need to know that where they meet forms what's called a bond angle. You need to understand that the covalent radius, or radii, is it's the radius of an atom when it's involved in a bond. And then you need to know that you can add up the covalent radii to come up with the bond length. Okay, so now that we have that foundation laid, it's now time for us to move forward, and it's time for us to start answering these questions. So we're going to talk today again about why do some atom pairings form salts, why do some form molecules, and why do some form the metallics. Well, guys, before we can have that conversation, the first thing we need to do is we need to define specifically what a chemical bond is. And so, guys, this is going to be our agreed upon definition. You don't need to write this down. You just need to remember the critical idea of attraction. That a chemical bond is, or chemical bonds are, attractive forces which hold atoms together when they form compounds. So atoms attract each other and they come together and they form compounds. So then the question becomes, when this happens, what part of the atoms are actually interacting in order to form the bonds? And I think that some of you already know that these forces happen when the valence electron clouds of two of these atoms interact together. So where do bonds form? And the answer is in the valence electron clouds. You may remember when we played around with this idea in the previous unit when we were drawing orbital filling diagrams, saying that oxygen has got two empty spaces in their orbitals. The hydrogens come along, stick an electron in each empty space, and that forms water. Well, guys, that's what we're talking about here. We're talking about valence electrons interacting, creating attractions that create bonds, which then create molecules. Well, guys, what you're going to find out today is that the type of bond that forms between two atoms depends on the characteristic properties of those atoms. Now guys, this then ties us back to what we talked about, the periodic table. So the idea is that in order to know the type of bond that forms, and therefore the type of compound that forms, salts, molecules, or metallics, what we need to know is the properties of the things that are reacting or coming together. And guys, this can happen in one of three ways. We could have a metal bonded with a nonmetal. And when that happens, we're going to talk about how that interaction goes and the type of compound that's formed. Then guys, another possible combination would be a nonmetal with another nonmetal. And if that happens, a different bond and therefore a different type of compound forms. And then guys, finally, lastly, we could have a metal with a metal. And if that takes place, then we've got another type of compound that's forming with a different separate set of properties. So guys, these are our three possible combinations: metal to nonmetal, metal or nonmetal to nonmetal, or metal to metal. And so guys, this lays out what we're going to do for the rest of the day. We are going to do these one at a time, talk about how these processes work and the compounds that are formed. Now guys, before we get started, allow your eye to look down at your notes page. You'll notice that this is also the organization of your notes page, the things that are in bold. So the first thing we're going to do is we're going to talk about a metal with a nonmetal. Then we're going to talk about a nonmetal with a nonmetal. And then we're going to talk on the back very briefly about metals with metals. And so guys, this then lays out for us the rest of the day. You'll notice on the back there is also a table where we're going to bring all this information together and summarize. And that then, guys, will be our day. Okay, so the first one we're going to do, as you see in your notes, is we are going to talk about what happens when a metal bonds with a nonmetal. Well, guys, to talk about this, what we need to do is actually answer three questions. You'll notice this isn't in your notes. You don't need to write it down. Right now, from here on, what you're going to be doing in your notes is you're going to simply be filling in the blanks. The hope is that that will take the emphasis off of writing things down and place it on the understandings. So guys, in order to understand what happens when a metal bonds with a nonmetal, we need to answer these three questions. What are the chemical properties of a metal? What are the chemical properties of a nonmetal? And then what do you think will happen when a metal and a nonmetal get together? So guys, let's do this to answer these questions. Let's go back to our periodic table. So guys, in doing this, let's first of all remind ourselves, what are the properties of a metal? And they are big, they are fat, they are weak, and they are electron losers. So these are big electron losers. Well, guys, what about the nonmetals? Well, they are small and they are strong and they are electron gainers. So, guys, these are our small electron gainers. So then the question becomes, what's going to happen when these get together? And guys, it's probably going to come as no surprise that when these get together, the small, strong nonmetal is going to grab a hold of the electrons from the metal, and the nonmetal is going to steal electrons from the metal. The metal is going to lose electrons, the nonmetal is going to pick up the electrons, and when that happens, a bond is created. So let's take that idea and let's dig into this a little bit deeper. So guys, when this happens, this is what is called ionic bonding. So why do we call it ionic bonding? Well, guys, remember what's going to happen. There's going to be a stealing of electrons. The nonmetal is going to steal from the metal. But guys, remember, when we gain or lose electrons, we form ions. So guys, that's why we call this ionic bonding, because we've got electrons coming and going, and that forms ions. Okay, so how does this work? Well, guys, the way that this works is a strong nonmetal steals electrons from a weak metal. And when that happens, ions are formed. Well, guys, remember, we're going to have a negative ion, which is the one that gains the electrons. And a positive ion, that'll be the one that loses the electrons. But then, guys, we already know that positives and negatives attract. When those positives and negatives attract, we form a bond, and that then forms a compound. Well, guys, these compounds have a name. These ions attract one another, they come and they bond together, and this forms salt. Now, guys, I know that in your world, in your thinking, salt is table salt, which is NaCl. And guys, that is certainly the case. NaCl is very, very much a salt. But guys, it turns out that it doesn't stop there. If you take a look, here's Na and here's Cl, and that is definitely a salt. But guys, you can take any metal and any non-metal and put it together and get a salt. So for example, one that we use actually in our lives every day would actually be lithium bonded to fluorine. And that actually gives us lithium fluoride. Sometimes we actually do this with sodium too, and we get sodium and fluorine making the salt sodium fluoride, and we put that in our toothpaste, and it actually makes the enamel of our teeth stronger. But guys, it doesn't stop there. We could grab a metal like strontium and a non-metal like nitrogen, and we just made another salt. That's actually what is called strontium nitride. So again, guys, it doesn't matter what the metal is. It doesn't matter what the non-metal is. A metal and a non-metal together forms what we call a salt. Okay, so coming back to this then, what I'd like to do is I'd like to then define for you a salt. And guys, a salt is simply a compound which contains ionic bonds. Okay, so let's take a look at what this process looks like. So guys, in order to do that, and you're not including this in your notes, let's take, for example, the metal lithium. Lithium is in group number 1. It's got 1 valence electron. That's a lithium atom. Now guys, over here, we have a fluorine atom. Fluorine is a halogen. Fluorine has 7 valence electrons. For this example, the Bohr model is just fine. But guys, remember, the fluorine is a nonmetal, the lithium is a metal, and the fluorine is strong. So what is the fluorine going to do to the lithium? Well, guys, if you watch the screen carefully, what happens is fluorine steals this electron from the lithium. When that happens, lithium lost an electron, it becomes positive. Fluorine gains an electron, it becomes negative. We all know that positives and negatives attract, and the lithium and the fluorine bond together into a salt, and that salt is what we call, again, lithium fluoride. So guys, anytime you have a metal and a nonmetal coming together, there's an exchange of an electron or more, and then these create ions, the ions attract, and we get salts. Okay, so that was our first of our 3 possible pairings, metal to nonmetal. So now, guys, let's move on, and let's talk about what happens when 2 nonmetals get together. Now, again, we've got 3 questions that we need to ask about this. So, well, actually 2 questions and a point. So, guys, the 2 questions we need to ask are, first of all, what are the chemical properties of a nonmetal? And then, what will happen when these 2 nonmetals get together? And then, guys, finally, we need to talk about this interesting idea, which is that when these 2 things get together, there's actually a couple ways that this can work out. So let's run over again to our periodic table, and let's first of all talk about the properties of nonmetals. So guys, when we have 2 nonmetals, well, let's just talk about nonmetals in general. Guys, remember that nonmetals are small and they're strong and they want to take in electrons. Now guys, imagine this. Imagine if you have 2 small, strong nonmetals and they want to start tugging on each other's electrons. Well, guys, the problem here is they are both small and they are both strong. And because they are both small and both strong, neither one of them wins, but neither one of them loses. The best analogy that I've ever seen of this is actually two little kids on a playground. Guys, imagine you've got two little kids on a playground and there's a ball that they both want. And both these kids are small, and both of these kids are stubborn, and both of these kids want the ball. And so one kid goes over and he grabs a hold of the ball and he says, "Mine, this is mine." But then another kid comes over and grabs a hold of the ball and says, "This is mine." And they're both small and they're both strong, and they both start pulling on the ball. Now guys, neither one of them is strong enough to win, but neither one of them is willing to let go. And as a result, what ends up happening is they are both literally stuck to the ball. Ready for the analogy? Now they're bonded together. They're bonded to the ball that they're both fighting over. Well, guys, that's exactly what happens in atoms, but the balls are electrons. Now, guys, the difference is this, that when this happens in the world of atoms, this can actually happen in one of two ways. See, guys, when this happens, this can either lead to equal or unequal sharing. And now you're going, wait a minute, we got kids fighting over balls. How is that sharing? Well, guys, if you think about it, it's kind of weird, but that's really what's going on. When two kids grab a hold of a ball and neither one wins, they're not sharing because they're generous. They're sharing because they're forced to share, because neither one of them will let go, but neither one of them wins. Well, guys, with that idea of sharing, we need to understand that this can either happen equally or it can happen unequally. So guys, let's talk about equal sharing first. So thinking about equal sharing. So first of all, sharing in general. Guys, sharing in general leads to what are called covalent bonds. Covalent bonds are bonds that are formed by the sharing of valence electrons. Now again, this can either be equal or non-equal. So let's talk about equal sharing first. Equal sharing, and again, gang, this is in your notes, just filling in the blanks. Equal sharing is what is called nonpolar covalent bonding. Now guys, nonpolar covalent bonding happens when two atoms of the same nonmetal bond together. So here's the idea. It's kind of a weird question, but if you think about it, it makes sense. Who's the only person that we can share with perfectly? And the answer, strangely, is our clone. The only person on Earth that's exactly the same strength as us, it would be a copy of us. Well, guys, the same thing is true in the world of atoms. The only atom that another atom can share with perfectly is another of the same atom. So 2 fluorines, 2 chlorines, 2 oxygens, 2 nitrogens. When they come together and share, they share perfectly. This is called nonpolar covalent bonding. This happens when we have equal sharing. Now, when we have equal sharing, this forms what we call nonpolar molecules. Now, guys, understand, this idea of polar molecules is going to become wildly important after Christmas. I'm introducing it to you now so that you have a general sense of it, but don't get caught up in this. We'll come back to this more after Christmas, but this is actually what this looks like. So guys, here we have a small nonmetal fluorine. And here is another fluorine atom, and we know that fluorine has got 7 valence electrons. So here are our 2 fluorine atoms. And guys, this is what it looks like when 2 fluorine atoms bond together. So what happens is the fluorine atom on the right starts pulling on the valence electrons of the fluorine atom on the left. And when that happens, one of these electrons moves towards the fluorine on the right as it tries to draw that electron in. But guys, then the opposite happens. The fluorine on the left starts pulling on the electrons from the fluorine on the right, and then that electron moves over, and now we've got a pair of electrons in between the two atoms. That's like the ball on the playground. So now we've got these two atoms that are fighting over these electrons. But guys, remember, neither one is stronger than the other. They're both strong, so they're not going to let go, but neither one is strong enough to steal. And what ends up happening is this. They literally lock together around that pair of electrons, and they come together and they bond by sharing those electrons, and we call that a covalent bond. But notice that it's equal on both sides, and as a result, this is what is called a nonpolar F2 molecule. Okay. Now guys, it doesn't always have to happen that way. We can also have sharing that is not equal sharing. We call this polar covalent bonding. This happens when we have different nonmetals that are close enough in strength that they share. So realize, guys, we're talking about still nonmetals. So they're both strong, so neither one can steal. They're both strong enough to hold on, but they're not the same metal. That means that they do not have the same strengths. This sharing is unequal. And guys, this creates what we call dipoles. Again, you're just getting this in your notes right now. But guys, understand that dipoles are going to be a hugely important concept, like polar molecules, after Christmas. But for now, guys, let's just say this. Dipoles are the partial charge on a bond that's caused by unequal sharing. So guys, what does this look like as we form these things that we call polar molecules? Well guys, let's do this. Let's trade out one of our fluorines for an oxygen. Here's our fluorine on the right, but now we've traded fluorine for oxygen. So now guys, turn your attention to your periodic tables. Notice where fluorine is, element number 9. Notice where oxygen is, element number 8. So guys, which one's going to be stronger? The fluorine or the oxygen? Hopefully you understand that it's the fluorine, because fluorine is on the right. It is therefore smaller. It is therefore stronger. So what does this look like when they start fighting over electrons? Well, guys, what's going to happen is fluorine is going to pull off one of oxygen's electrons, but then oxygen is going to pull one of fluorine's electrons. But notice the difference. Notice where the electron pair ends up. Do you see that it's closer to the fluorine? Do you understand why it's closer to the fluorine based upon their strengths, their electronegativities? So guys, fluorine is stronger than the oxygen, so the electrons end up closer to the fluorine. Well guys, understand that what that does when these atoms then close down on this pair of electrons is literally we end up with a bond that is lopsided. The bond is shifted towards the stronger fluorine. But guys, because these electrons are negative and the negatives are closer to the fluorine, it makes the fluorine the negative and then the oxygen the positive dipole of the bond. Again, guys, this idea of dipoles is something that we're going to talk about later, but just understand right now, the idea is these electrons are closer to the stronger fluorine, and that creates a lopsided bond, and therefore what we call a polar molecule. In this case, that would be an oxygen fluoride molecule, and that thing is in fact polar. Okay. So guys, we've got one more to go. We've now done a metal with a nonmetal that is stealing ions, ionic bonding, and salts. Now we've done two small, strong nonmetals together. When they come together, they don't steal, they share. We call that covalent bonding. Covalent bonding can either happen equally if the two atoms are the same, or unequally if we have two different nonmetals. So guys, now what we need to do is we need to talk about the last pairing, and this is a metal with a metal. So again, the question that we are starting with is, what are the chemical properties of a metal, and what are they going to do when they get together? So guys, again, looking at our periodic table, we've got all of these elements over here, which are the metals. And guys, metals are big, and they're fat, and they're weak, and they just want to give away electrons. So the question is what is going to happen when you get a bunch of metal atoms together? Well, guys, we already understand the idea that metal atoms are going to lose electrons. But if all we have is metal atoms, where are the electrons going to go when the metals lose them? And guys, this is where this gets interesting. So the question is, where do the electrons go when the metals lose their electrons? And strangely, watching the screen carefully, where do the metals go, or the electrons go? Strangely, the answer is everywhere. Guys, keep your eye on the valence electrons. And this is literally what happens. These valence electrons just get dumped into the spaces in between the atoms. They literally just form this puddle of electrons that these nuclei are bouncing around inside of. But guys, notice what happened as this took place. Every single one of these lithium atoms lost an electron. That means that all these lithium atoms are now positively charged. They're ions. Well, guys, what about all the space within the atoms? Well, that's all full of electrons, and all of those electrons are negative, watching closely. And guys, we describe this as a sea of electrons. So if you turn your notes page over on the back, metals with metals, we get a sea of electrons. Guys, this is actually what makes metals very, very conductive. All electricity is a flow of electrons. And when we make a wire out of metal and we plug it into a socket, guys, literally what happens is electrons flow out of that socket into the sea, and they just pass right through the sea, and that's actually what makes metals conductive. So the way that we look at it is we look at it like this. This is actually lifted out of my AP book, and we describe this as being a sea of electrons where we've got these positive nuclei bobbing around in a sea of negative charge. So guys, there you have it. We have now gone through the three types of compounds that exist. We have salts, molecules, and the metallics. We understand how they form. We understand what atomic pairings form them. So what we're going to do now is we are going to create a table that will allow us to review all of this material. And so guys, what we're going to do is we're going to talk about the types of bonds. You already know those. They are metallic or ionic, covalent, and metallic. We're going to talk about the atoms that form them, how those bonds form, and then the properties of the things that form those bonds. So guys, first of all, let's fill out the left-hand side of the table. We've got ionic, we've got covalent, and we've got ionic, covalent, and metallic bonds. So we're going to start first with ionic, and let me give you a second to catch up. So we've got ionic bonds, which involve stealing, covalent bonds, which involve a sharing, and then the metallic bonds, which is just the turning loose of all these electrons in metals. Okay, so guys, let's work our way to the right. So again, what atom pairing forms ionic bonds? Well, ionic bonds is stealing. Who can steal from the other? And guys, stealing happens when we have a metal giving up electrons to a small, strong nonmetal. So what is the mode of formation? How does this happen? Well, this happens when we have an electron transfer, and this creates ions. These ions then attract, and this forms salts. And again, guys, examples of salts are things like lithium fluoride, which we saw in the animation, sodium chloride, which you know to be table salt. Calcium iodide is another example of a salt. Any metal with a nonmetal forms a salt. Now, there are some properties that you need to know of salts. So guys, salts contain ions in all phases. Whether it's a solid, a liquid, or a gas, there are ions inside of salts. Now guys, their solids do not conduct electricity. Their ions are trapped in place and they don't conduct. But their liquids do. We'll talk more about that later. But guys, they also have very, very high melting points. If you don't believe me, go home tonight, get a saucepan, fill it up with table salt, put it on the stove, and try to get it to melt. Guys, you can't get salt to melt at home. You can't create enough heat or high enough temperatures to get salts to melt. The reason is simply because of the strength of the ionic bonds that exist inside these salts. Okay, so let me pause for a second, let you catch up. Then guys, let's move down and let's talk about covalent bonds. As we know, covalent bonds are formed by two nonmetals. If they're the same nonmetal, that's nonpolar bonding. If they're different, that's polar bonding. So how does this work? And it's a sharing of electrons. When we have electron sharing or covalent bonding, this forms what we call molecules. Examples are things like carbon dioxide, water, and also sugars and fats and proteins and things like that. Giving you a second to scratch this down. Guys, if you're being careful about what you're writing down, you should have a big problem with something that you just put in your notes. So guys, let's talk about it. Water. Find oxygen and find hydrogen on your periodic table. So we're talking about covalent bonding, which is two nonmetals bonded together. And if you find oxygen, element number 8, that's a nonmetal. But now find hydrogen on your periodic table. Guys, that's a metal. It's on the left-hand side of the periodic table. So you're like, wait a minute, shouldn't that be a salt, an ionic bond, because hydrogen is a metal? And guys, the answer is no. This is the one exception to the things that we just learned. Hydrogen is different. Hydrogen is a freakishly strong metal. Hydrogen is a metal, but it is such a strong metal that there are very, very few nonmetals that can steal from it. So guys, when you see hydrogen, you need to be thinking this is an exception to the rule, and hydrogen does not form salts, forms molecules. Now, the things that you need to know about molecules. Guys, molecules they don't contain ions. There's no exchange of electrons. They have low melting points. Guys, think about that. Sugars, fats, water, already melted at room temperature. Guys, they have very, very low melting points. You could go home tonight, you could take a sugar, put it in a saucepan, put it on your stove, and the sugar would melt. That's how we make candy. Sugar and other covalently bonded molecules have low melting points. And because they don't contain ions, they insulate in all phases. All right, so last but not least, we have the metallic substances. These are formed by metals. The mode of formation we say like this. a delocalized, without location, a delocalized sea of electrons around a weak nuclei. That's the whole idea of the sea of electrons. Delocalized, spread out sea of electrons around these weak nuclei. So guys, these then are the things that you need to know about the metals. They conduct. You may remember we talked before about them being ductile. That means you can pull on them like taffy and they stretch without breaking. They're also malleable. It means if you hit them with a hammer, they smush without shattering. They're shiny. Light reflects off of that sea of electrons. And then guys, finally, they have very high melting points. It's hard to get metals to melt. Some of them, others not, but they do have high melting points. All right, so gang, there you have it. That is everything that you need to know to get settled with these ideas of bonding and elements and metals and nonmetals and compounds. What we're going to do then to wrap up the day is we are going to do homework assignment number 2. So grabbing your homework packet, we're now going to do assignment number 2. You'll notice that it's 2 pages. We will look at this when we get back together next time. The answers, of course, are posted on our website. So give them a look, and I look forward to seeing you when we all get back together next time. Thanks and have a great day, y'all.